One bourbon, one scotch, and one bill. One bourbon, one scotch.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. Our friction example asks the following question. We would need to pull this box at a constant velocity on the surface with some friction. And the question is, what angle alpha minimizes the tension force in the rope that we are pulling it with? And why is this so? So there's of course gravity acting down and some normal force N. And as we learned, the friction force F mu depends on the N, and N depends on the amount of tension force that we have in the y direction. So the T can be divided in two components. Here's the vertical one, so this is going to be T times sine alpha, and then the horizontal component is T times cosine alpha. So depending on the angle, the value of T required changes, and we would like to find the minimum value. We solve this problem just by using Newton's laws. This is a static problem because there is no acceleration, so we stick with Newton's first law, first of all in the x direction. So what do we have in x direction? The tension horizontal, T times cosine alpha, minus the F mu, the friction force. And because this is moving at constant velocity, the net force is 0. Let's leave that for now, and then we'll look at the horizontal or vertical direction. And of course we had positive direction to the right, and let's also define positive direction to be up on the vertical axis. So in the y direction, the sum of forces is N positive plus T times sine A, and gravity is in the negative direction, and net force here is also 0. It's not accelerating in the vertical direction. And we'll solve N from this equation, so the amount of normal force from the surface. So that's going to be just mg minus T sine alpha. If you go on this side, we can note that F mu is coefficient of friction times the normal force. So we have T cosine alpha minus mu n equal to 0. And now if we substitute the n from here, we get T cosine alpha minus mu times mg minus T sine alpha. And opening that thing up, T cosine alpha plus T sine alpha times mu, and minus mu mg, so we move the mu mg to the other side like this. And from here we get expression for T. So that's going to be mu mg divided by cosine alpha plus mu sine alpha. And here we see what I claimed in the beginning, that the tension force depends on the angle alpha. And how do we find the minimum? So first of all, let's say that the alpha has to be somewhere between 0 and 90 degrees, so that we are pulling to the right. And at the maximum case, we are pulling it straight up. Of course, it doesn't make it move horizontally, but it definitely minimizes the friction force. But anyway, so that's our those are our limits, and we try to find if there's a minimum somewhere in between. So the function can always have its minimum at the these endpoints, or somewhere in between where the derivative goes to 0. So let's evaluate the derivative of this one respect to the quantity of interest, that is angle alpha. So it's going to be derivative of the numerator, which is 0, times this function, so cosine alpha plus mu sine alpha. Well, the whole thing is of course 0, so we don't care about that, minus derivative of what we have in the bottom. So derivative of cosine alpha is minus sine alpha, and derivative of that one is mu cosine alpha, and this times the whatever you have on the top, mu mg, and whole thing divided by the second power cosine alpha plus mu sine alpha squared. Let's clean this up a little bit. So we only have umg times sine alpha let's make clear that's plus minus mu cosine alpha, and then the denominator squared. And when is this derivative 0? Well, when this one goes to 0. So we get sine alpha equals mu cosine alpha, or mu equals sine alpha over cosine alpha, which is same as tangent. So alpha can be solved to be the inverse tangent of mu. And in our case, mu is, let's say, 0.4. So inverse tangent of that is 29.8 degrees. And to compare some numbers, let's give it a weight. So if this is about 50 kg box, so mg is about 500 newtons, and we can use this expression to evaluate the numerical value. So if we plug in the numbers, so t at 0 degrees when it's horizontal, that's going to be 200 newtons. T at calculated 21.8 degrees is about 186 newtons. And if we go all the way vertical, and pretty much we are lifting it up, then of course the tension force would be 500 newtons. So we have our minimum nicely there, around 22 degrees.